Okay, class. Assalamualaikum warahmatullahi wabarakatuh and good days. Today we're going to continue our chapter 3 on trade distribution. Previously we have covered trade generation. Okay, in trade distributions, we're going to look into this origin and destination. So typically we're going to use metric table to calculate for each zone from origin to destination. This is the typical metric table to calculate trip from origin, also trip to destination. Okay, typically we're going to use iteration method for calculate for each cell. Okay, also we're going to check metric balancing between production's outcome and also attraction in terms of the three numbers. Okay, this to be balanced. If you calculate the total, it to be balanced. Okay, this as well. We're going to check the number of the total from production and attraction. This is going to be balanced. So for this individual value for the trips that lead to the production and attractions. So simply we're going to multiply the first value from the total of the productions. So this one to represent attraction. This one production. Sorry. Okay, multiply by this one. So divided by total. So you're going to apply this technique, typical technique, to obtain this value. Okay, the basic formula that we're going to use in this trip distribution is a gravity model. So they inspired by the first gravity model, but we transform into a trip model. So we have a trip, also the production, attraction. So this K is the constant, okay, multiplied by attractiveness or the function that relate to the trip. Okay, if you have a constraints, production constraints, so we add some more function. Like this one, we have some more function. Okay, for attraction, so we're going to use this one. Okay, double constraint, so we can put into additional value to represent this kind of the double constraint. So before we going to go example of the or detailed explanation for trip distribution, first we just revise the trip generations, which is we have zone, coordinate line, and divided by zone. So socio-economic, which is household income or vehicle ownership, land use data, number of unit housing, industrial office. So this one is traffic zone. So let's say we have 8 zone. This is production, the typical one, just example. Okay, another one is attractions. They also have a number of trips by attraction. So the output will be the M trip by trip purposes. Okay, from trip generation that we have this one. So we're going to move to trip distribution. Why do attraction in zone 1 come and where the production go? Okay, where do trip produce? Each zone will be go and how they will be divided among all zones in the study area. So this one first, zone 1, this one. So they're going to move to zone 2, 3 up to 8. Then we're going to use this distribution metric. So by using this formula, this input data using gravity model. Okay, let's move this example. So we have at the TAZ3, so total number attraction estimate in the trip generation, step for house base work trips. So starting from TAZ3, so they have attraction to no, production to attractions. So from 3 to 1, 3 to 2, 3 to 4, and 3 to 5. They have travel times and also trip numbers. This one have production numbers. So we link production and origin zone to attraction or destination zones. Okay, a trip metric is produced. So we just tabulate the zone into this one and this one. Okay, the cell within the trip are interchange zone between zone. Okay, basic assumption of the trip distribution. The number of the trip decrease with the cost between the zone. Okay, number of trip increase with the zone attractiveness. Okay, the model of distribution. First they have factor model. After that they have gravity model. So we're going to look detail in the gravity model exercise. Also we're going to cover a little bit on this growth factor model. Okay, for growth factor model, growth factor model assume that we are already have a basic trip matrix. So you have this one. So after that, we will obtain the previous study or recent survey data. Then the goal is to estimate the metric at some point in the future. For example, what would be the trips look like in 2 years time? So let's say we have this scenario or this data on 2008. So what would be the 2 year next? So we're going to predict this one using growth factor. So first we have uniform growth factor, single constraint growth factor, average factor, detroit factor, and Frata method. So for uniform growth factor model, so we just go for the definition, the indicator for the function of formula. So I represent production zone. So J represent attraction zone. So T is the trips, that we can consider from the production and attractions. So this is the factor. Okay. This one the trip metric that we're going to calculate based on this value. Okay, Tij base year trip matrix. Okay, this one the factor growth. Because we're going to use the growth factor, but in the method of uniform. Okay, let's say we assume the tau, the factor for the growth factor is 1.2. So we just assume 1.2. Okay, this is the existing, let's say existing in 2008. So what would be the trip metric or the trip distribution in next years, next futures, on the futures. So we're going to use this simple formula for the uniform growth factors. So we already given the tau, and this one refer this one. This ij refer to this individual cell. Let's say we move to the first one, attraction and production, which is I and J. So 1.2 the factor multiplied by first cell 5. So that first cell will become 6. So for the next, just repeat this procedure, like doing the iteration for each cell by individual using this formula. Just insert the growth factor 1.2. Let's say you want to predict this one. So just use 1.2 multiplied by 5, then we obtain 6. If we want to predict this one, let's say 4 and 2, 4 and 2, or 2 and 4. just insert this 300 multiply by 1.2, you obtain 360. That this very typical and very simple way to calculate a future using uniform growth factor. Okay, the uniform growth factor is typically used for over 1 or 2 year horizon. However, assuming that the trip grows at the standard uniform rate is fundamentally flawed concept. Okay, that is why we're looking to use gravity model. So the big idea behind the gravity model is Newton's law of gravitation. Gravitation, this one, the basic one. So the force attraction between two body directly proportional of the product masses between the two body inversely proportional the square of the distance. So in the gravity model, we do have quite similar function, which is Tij. Also, we can represent Q as well, just to make a different between production and attraction. Okay, now we have the function or the additional factor for friction factors, which is we represent Fij 1 divided by Wij. So W is generalized cost including travel times and cost. Okay, C just a calibration constant. Okay, Pi the total number of trips produced in zone I. So this one is the capital P. So small p is probability of probability that trip I will be attracted to zone J. So Kij socioeconomic adjustment factors. So these are the full of gravity model to be used. So whether going to use T or Q or P depend what we're going to predict or what going to be calculated. So this one Pi is production, A is attractions, F is friction factors, K still under the friction under the factors. Okay, this one does remain quite the same. Okay, Fij, which is represent I just explained just previous slide. Okay, the biggest friction factor, the more trip that are encouraged. So these are the reference for using the friction factors. Friction factors value. So within this travel times in minute, so we're going to refer these friction factors. Okay, this also refer the type of the trip. What base? Non-work base, home base, work base. This typical graph to be referred to obtain the exact suitable friction factors to be used. Okay, the greater separation between origin and destination, the less likely trips, the larger places, the greater attraction. Okay, to apply a gravity model, what we need first production, then attraction. So we have to have this kind of the data available. Okay, and we apply scheme table. Okay, and the target interzone, the target year interzone impedance. So let's move to this example. So given target year productions, relative attractiveness zone and scheme table, and they give a C factor for 2.0. So social economic factor that K is 1. So the question just find or calculate the trip interchange, which is Qij. Okay, let this we have this example. So we have 4 zones and represent for production, and 4 zones as well represent attractiveness. So we have this trip and where's this the number of this attractiveness. Okay, we have also the distribution scheme table. Okay, given collaboration factor 2.0 and social economic factor is 1.0. So first one, we have to calculate the friction factors. So friction factor, if we just go back to the previous slide, which is I divided by VC, WC, sorry, WC. Okay, this one, 1 divided by WC. So C given, okay, just a factor letter we're going to use. So this one is very straightforward, but we have to be careful with the metric, which cell we are referred to calculate the numbers. Let's say we give example to this value 0.04. So just add this value from this one. So we have cell 11, cell 11. So W is given here, which is 5. So we have correction and calibration factor 2, so we obtain 0.4. And you can calculate the rest. You can refer to calculate to obtain the value for each cell. Okay, next we're going to determine the denominator factor of gravity, which is attraction friction factor, and K is given. Okay, here we can calculate this one by using this formula. Okay, but be careful. Again, you have to refer specific cell to obtain the correct value. Let I give some example. 0.05. How to get this value? Okay, first refer to this formula. Okay, 5. Here, 5. I just give this one. Table 3 to 4, or 4 to 3. Table 3, 4, 3, 4. Okay. I can use the pointer. Okay, this value 3, 4. So 3, 4. So first we refer this table, which is attraction. 5, 4. This one 4, 4. A 4, 5. Okay, 0.01 we just obtain here 3, 4. Here, this one this one 4. You can refer here 5. This 0.01. 3, 4. 3, 4 here 0.01. 1 is the factor, given factor. Then we obtain 0.05. Okay, that's the procedure. Okay, next. Finding probability trip will be attracted to zone J, which is P. So P, the probability to be calculated using this denominator, gravity model equation divided by summation, which means total. Okay, let's put this example. Okay, how to obtain that? Okay, first we just obtain the value of 0.05. So given here, we obtain here. Okay, next, this one, just the summation, just the summation of the value here. We focus on table 3, 4. So here we have 0.06, 0.16, sorry. Now we obtain 0.05 divided by 0.16. So we obtain 0.3125. The next, we're going to find QI, the last one, the trip set. The trip set. This one is a trip distribution for the Q. So how to calculate this one? So this one just we just obtain from the Q that we calculate from the given value from here. So you just go back to check the calculation for the Q itself. Okay, keep in mind that socioeconomic factor K can be metric of value rather than just one value. Okay, it can be previous, not just a single value like with previous example 1.2, but we can choose any other K factor for different different zone, and also different reference value, not just fixed value. Okay, the problem with K factor, although K factor may improve the model, in the base year, they assume that these special conditions will be carried over to future and scenario. Okay, this limit model sensitivity and undermine the ability to predict future travels behavior. Okay, the need for K factor often is the symptom other model problems. Additionally, the use K factors make it more difficult to figure out to the real problem. So these are the limitations of the gravity model. Too much reliant on the K factors in calibration, external trip and interzonal trip cause difficulties to the skin table. In impedance factor are often too specific to be realistic. Typical based solely upon vehicle travel times. Okay, at most, this might include toll and parking costs. Almost always fail to take into account how the things such a good transit and walkable neighborhood affect trip distribution. So this part of the reality that happen into uh, distribution activities or trip distribution value. So no obvious connection between behavioral decision making. So we move this again, this example. So now we look how to apply these friction factors value to calculate the trip distribution. Okay, if we look this T as T Z, okay, which are the trip produced in T as tree go. So we have a distribution here. So now convert travel time into friction factors. So previous slide I just showed the graph for friction factors. So this one is typical for home-based work. Home-based work. Okay, they have a travel time here and value of friction factors. So if you have a very less time in the travel time within short time, so friction factor going to be greater or larger value. If you have more travel time, so your friction factor to be less. Okay, in for these particular problems, so we have a travel times for individual. So now we can use this friction table, which is 20, 7, 10, and 35. So we have here 20, 7, 25. So we just add the table to be this form. So table 1, we have at zone 1, which is 20 minutes. So friction factor now 6. Okay, zone 2, we have a 7, so 25, and so on. So we're going to transform this particular question into this table. Okay, next we're going to calculate attractiveness of each zone. So attractiveness equal to attraction multiplied by FF. So FF is friction factor. So we're going to determine which most zone are attractive. Which one? So based on this particular calculations, so this very simple one. Just calculate attraction multiplied by friction factors. So here we just notice that zone number 2 has higher attractiveness, which is more than 15,000. So these are the value refer here to just represent not the attractive zone. The most is here, but this one is typical to represent that we have 47 attraction and the friction factors. So from here we can insert the value for friction factor, but this is not indicator for attractive zone, but attractive zone is here. So the attractive zone actually here. This just example to relate from this figure, refer to this data. Okay, to calculate relative attractiveness of each zone. Previously, we just calculate attractiveness. This one is relative, which is A multiplied by FF divided by summation of A multiplied by FF. So again, we just obtain the value of attractiveness, previous calculations. So now we want to calculate the relative attractiveness. Just divided the number of the attractiveness divided by summation of the attractiveness, which is 26,473. So now we obtain the value for relative attractiveness. So we can see here the relativeness index higher is zone 2. So because zone 2 they have very shorter travels time. Then they attract more trips, and also the relative attractiveness is dominant. Okay, distribute progression to TAZ, to all TAZ. So we're going to calculate the distributed trip, which is T. T. Okay, T equal to P multiplied by the relative attractiveness. Okay, so first we have P, which is production from the figure example, which is 602. So this one, the production, and the attractiveness value. So we can calculate for this one. Okay, then the trip and the trip distributed value. So for each zone, that going uh, to be calculated. So first one, 147, 350, 78, 19, and 8. So we see here that's the most distribution trip in the TAZ2, from 3 to TAZ2, which is more trip. Okay, other example, trip distributions. So from here, also they use quite similar but distant function rather than friction factors. So here also we can calculate the trip distribution. So like here, from the zone 1, zone 2, and zone 3. So we use the typical trip distribution formula. So we can calculate the trip numbers. Okay, example 3, zone production and interactions, which is this table, and the time travel between the zone. So here, and they given the friction factors value. So based on this one, we have to use the friction factor letters, but they given also the travel time for individual zone matrix. Okay, from that particular table data, so here we have zone 1 to zone 3. So we have a trip production and track action. So now we calculate for each trip for cell. This one, that cell 1, 1, 1 to 1, 1 to 2, 1 to 3. Okay, the first one we obtain. So this one is the 1, 1, 1. Okay, 3, no, 300. So this one is production P. So just refer this formula. Sorry, this formula. Okay. Okay, 39. Here we have travel zone of 5 minutes. Okay, this one 207. This one 52. So travel time 2. 52 here. Travel time 2 minutes. 52. So 100 multiplied by 50. So 50, this one 3 minutes, 3 minutes, so 3 minutes. So now we obtain the Q1 one is 47, Q1 2 is 57, Q1 3 is 36. So here we going to start the iteration. This one just typical example for this one. For the rest you have to calculate this one. The procedure quite similar this one. Refer this table and this table as well to obtain the exact value for friction factors. Okay, after that we're going to have this typical or this total individual trip for this given. Okay, this one the summation of the trip production. Okay, okay, compute A, which is we get total, but in terms of the given data 307, 220, 270 and 180, this one is original data from this one 300, 270, 180. Okay, this one refer to this one 140, 330 and 280. Okay, so there is some differ value if you compare this one, but the total is still same. So how I'm going to solve this problem? You have to do the next iteration. You have to do the next iteration. So second iteration, by using this attractions, which is kj multiplied by kj q1 divided by c which is actual attraction total for zone J and section K. K adjusted action factor for attraction zone. Okay, so this one is the correction to be applied. So we just apply the K value to recalculate to balance from the predicted compared to origin data. So the first one K11 we obtain 237, K12 347, K131 201. So we just add the new value here, to calculate the T. So now we obtain 34, 68, 37. So we're going to calculate again. So the procedure quite same, but this the second iteration. So we notice that the number here is going to be close. Going to be close. So you can proceed into iteration 3 if you want. But this consider is quite close. So we can stop here, or you want to go more further, you can. until you reach quite a similar value. But until then, it's quite acceptable to obtain this quite comparable value. Okay, I think that's all to cover trade distribution part. So I will proceed for model split for the next lectures. Uh, I think next week, not this typical week. Okay, you have to cover this one first because there is a lot of the procedure. I will give some additional exercise to strengthen or to have better understanding to apply trade distribution application or trade distribution model calculation. Okay, that's all for today. Thank you.